Hi everyone, welcome to this video. So in this lesson, we go to topic 5, work, energy and power. In this video, we go to 5.2, energy and conservation of energy. So what is energy? The definition of energy is defined as the stored ability to do work. Energy is a scalar quantity, and you need to know the SI unit for energy is joules. That's capital J. There are two types of mechanical energy, kinetic and potential. First one, we go to kinetic energy. You can write down the symbol capital K. The definition of kinetic energy is the energy of a body due to its motion. So that means any moving object has kinetic energy. You can write down the equation of kinetic energy as half mv squared, where K is kinetic energy of a body, M for the mass in kilogram, and V is the speed of the body in meter per second. Kinetic energy is a scalar quantity, and that means that kinetic energy depends on its mass and speed, but not direction. The next type of energy is the gravitational potential energy, which you can write down as the symbol capital U. It's the energy stored in a body or a system due to its position. You can calculate the gravitational potential energy using the equation U is equals to mgh, where m is the mass of the body in kilogram, g is the acceleration due to gravity, that's equals to 9.81 meter per second squared, and h is the height of the body from initial position. Next type of potential energy is the elastic potential energy. It is the energy stored in elastic material as the result of the stretching or compressing. You can calculate the elastic potential energy using the equation U equals to half kx squared, where k is the spring constant and x is the compression or extension of the spring. Let's see in more detail what it means, compression and extension of the spring. Alright, let's see this picture. In the middle, you can see the spring is at the equilibrium position, where we call it x equals to 0. And this is the position where there is no external force on the spring. And at the top is when the spring is stretched by a distance x. So the spring is stretched by the external force F, and the Fs is for the restoring force. And at the bottom is when the spring is compressed by distance x, so the value of x is negative. So now we go to Hooke's law. Hooke's law states that the force required to compress or stretch a spring is equals to negative kx. The negative sign is because to indicate the direction of the restoring force is always opposite to the direction of the displacement. So this equation Fs is the restoring force of the spring, K is the spring constant with the SI unit Newton per meter, and X is the amount of stretch or compression. You also need to know for calculation you may ignore the negative sign. So let's recall back. We have learned that we have force versus displacement graph. The work done is the area under the graph. So to calculate the work done, it's the area under the fx graph. So since the shape is a triangle, so you calculate it using the equation half times f times x. So the restoring force is kx So that gives you half kx squared. So this half kx squared is the elastic potential energy in the spring. And that is because work done is stored as the elastic potential energy in the spring. So now we have found out the relationship between work done and the energy. So let's see the relationship between work and energy. So this leads to the work-energy theorem. It states that the work done by the net force on a body equals the change in the body's kinetic energy. Or to put that into equation, the net work done is equals to delta K, where delta K is the change in kinetic energy. So the final kinetic energy minus the initial kinetic energy, or half mv squared minus half mu squared. It was to note that the net work done is positive if the kinetic energy increase or if the particle is going faster. And vice versa, work done is negative if the kinetic energy decrease or the particle is going slower. And the net work done is zero if the kinetic energy stays the same or the speed is constant. So let's learn about the principle of conservation of energy. It's probably one of the most famous laws in physics. It states that in an isolated or closed system, the total energy of that system is always constant. To put that into a formula, the summation or the total of energy initial is equals to the summation of the final energy. So energy can be transferred or energy can be transformed from one form to another, such as from mechanical energy to heat energy, but it can never be destroyed or created. The same law applies to the principle of conservation of mechanical energy. It states that in a conservative system, for example, no friction, the total mechanical energy, which is kinetic and potential, is always constant. So the total potential energy initial plus the initial kinetic energy is equals to the final potential and kinetic energy. For example, if a boy want to drop a ball to the floor, so at the first position, there is only potential energy, the gravitational potential energy, because there is no movement. So in the middle, there is half potential energy and half kinetic energy. And at the final position, number 3, just before it hits the ground, there is only kinetic energy, while the potential energy is 0 because the height is 0. Example number 2, when you load a bullet inside a gun and the spring is compressed, there is elastic potential energy. And after that, when the bullet is fired off the gun, elastic potential energy is converted to kinetic energy. So in this situation, energy is conserved. However, in real-life situation, friction is involved. The friction acts in the system in the direction opposite to the direction of motion. So the initial mechanical energy of the system is equals to the final mechanical energy of the system plus the heat energy due to work done by friction. Sounds like a long statement, but to put it in a simpler equation, the total kinetic energy plus the potential energy, initial potential energy plus the work done by friction force is equals to the total final kinetic energy plus the final potential energy. Let's try a sample question. A roller coaster car, as shown in the figure, is pulled up to point 1 where it is released from rest, assuming no friction. Calculate the speed at point 2 and 3. So first you want to label the energy which is involved at each point. So at point 1, there is only gravitational potential energy because the object is at rest. So there is no kinetic energy. And at point 2, there is kinetic energy but no gravitational potential energy because height is 0. And at point 3, there is both gravitational potential energy and kinetic energy. So let's apply the principle of conservation of energy. So the total energy at point 1 is equal to the total energy at point 2. So mgh is equal to half mv squared. So substitute, g is 9.81, height is 32, and you can cancel out mass on both sides. So that will give you V2 is equal to 25.06 meter per second. And for point 3, you can use point 1 or point 2 as the initial position. So let's say use point 1 is mgh. So at point 3 is mgh plus half mv squared. So substitute all the values. G is 9.81, height 1 is 32, and height 2 is 14. And you can cancel out the mass on both sides, and that gives you V3 is 18.79 meter per second. So congratulations, you have completed 5.2 energy. Thank you for watching.